All right, video 2 on switches. We're going to talk about what we need in order to make a switch work. So let's jump into it. And the key here is pull up or pull down resistors. So the last video we talked about three kind of main types of switches here. Actually, two main types, which are our momentary and our latching switch, and then kind of a special case, which is our tilt switch. If you want to go see that video, it should be in the description. Okay, so we would think that if we were attaching a switch to something that took a digital input, and I'm just writing that here as DX, some digital input. On an Arduino, it's going to probably be a digital pin. So digital pin 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, or one of the digital pins that we have on our Arduino. Generally, we're going to attach a switch to it. Now, you would think, okay, I have a signal. I'm looking for that signal with this switch, with that digital pin. So on that digital pin, generally we're going to say, okay, this pin, first we're going to tell the program it's going to be an input, and it's going to say, okay, I'm looking for some voltage here. I'm looking for some signal. And if I see that signal and I say, okay, this is a high signal, then I know, like, okay, I have a signal, and now I do something since I'm seeing this. And if it's a low signal, then maybe I don't do something, or maybe I do. You can program it however you want. The point is, we need this digital pin here to be able to see whether it's getting a high signal, as in 5 volts, or a low signal, as in 0 volts. So in this case, you see that I have this labeled as this is the wrong way to do it. You may say, well, why is that the wrong way? That seems pretty straightforward. I have 5 volts going in here. If I don't have 5 volts, then this sees 0 volts, and it says it's off. And you would say, okay, well then if I close that switch, then I have a good line for current to run into it, and then it sees 5 volts at that digital input, and it says, okay, I have 5 volts, so now my input is technically high. Well, that's close. So the problem here is that a digital input is looking for either a 1, which is a high voltage, in this case 5 volts, or a 0. It is either fully on or fully off. There is no real in between. And it has kind of this range of values where it says, yep, we'll consider this on, and that is between 3 volts and 5 volts for an Arduino. This might vary depending on the microcontroller you're using, but if you're using an Arduino, 3 volts to 5 volts, it's going to say, yep, this is a high voltage, our switch is being activated, and we know that at our digital input, we are getting our voltage that's necessary to consider it on. So anywhere in this green zone here, that is a high signal. We know that we're getting the voltage that we need. Now, similarly, from 1.5 down to 0 volts, that is our low signal range. And you can kind of start to see the problem here. If, for some reason, we have some signal in between, somewhere in here, it's not really going to know, and it's kind of just going to guess. It's going to say, well, I think it might be a high signal or it might be a low signal, but in that case, it's undefined. So it doesn't really know whether it's a high signal or a low signal. You can say, well, I mean, I don't understand how that could really happen here. Well, it turns out Arduinos have a lot of traces, or they have a lot of different circuits that are running right next to each other. And those, if we have a circuit running here and a circuit running there, or even just circuits running around our digital input, we can get a lot of interference there and get what's called a floating input. And our floating input says, well, it kind of doesn't know whether it's high or low, especially when our circuit is open. And that's because even just changes in the capacitance of stuff in the air, and even moving your hand over the top of your microcontroller if you don't have it built up the right way, will tell this, like, oh yeah, we might be in this high voltage range. And then moving your hand away probably puts it, oh, we are moving around here, probably puts it back down into like this ambiguous state, and then maybe it puts it down into low, and it kind of just has this weird voltage, and it's not really sure where that voltage is actually at. So we need some way to mitigate that and say, like, you are absolutely getting a high voltage or absolutely getting a low voltage. So in this case, we're not really sure. Are we getting a high voltage? Are we getting a low voltage? There's all sorts of stuff interfering here, and we're trying to figure it out. So that is why we install what's called a pull-down resistor. resistor. You can have a pull up resistor, and I might go over that in a separate video, but in this case, we're just going to talk about a pull down resistor. In this case, our pull down resistor is going to be a 10 kilo ohm resistor, 10K. So 10 kilo ohm resistor, and I'll talk about kind of why we're using a 10 kilo ohm resistor. Really, it's just a good value in terms of the voltages and current that we're working with here. It's going to give us a really good ratio. So this is the circuit that we're going to need, and this circuit is going to tell us why, or exactly whether or not this is a full 5 volts or not. So if we're, again, looking from the perspective of this digital input, and we're saying, okay, what am I receiving here? What can I tell that I'm connected to? Well, it's going to see, essentially, that it's connected, and the only real connection in this case, because we have this open circuit, and the only real connection is directly to ground. Even though we're going through this resistor here, that resistor is the only path for current to take, or the only reference that this can see. Now, you might still get some interference out here, and interference, from different circuits, but this connection here, even though we have a high resistance through this connection, it's still going to be much, much less resistance than we have in the air or different things surrounding it. So it's going to be a much stronger signal through this. And we're going to see on this digital pin side, okay, if this thing is open, I am connected to ground. And that is the one thing that I can see is almost a perfect 0 volts. Now, if we go over here and we look at this case, it might vary a little bit, and it's going to jump up and down like this, but it's going to stay pretty close to 0 volts, well within this threshold here that we have for a low signal. And the reason that it would jump up and down, again, is because of a little bit of interference. But again, that interference, very, very low compared to our strong signal, relatively strong signal through this resistor. So let's look at the case where we close this. So we're going to close this circuit. I'll erase this here, and we're going to pretend like this is a wire. So now we have a perfect closed circuit. Well, now we have a path for current to flow from our 5 volts into our digital pin. And our digital pin is considered an input, so it is low potential at this point, meaning that current wants to flow into it. So it actually comes over here, and we have current flowing this way, and then current has 2 paths that it can take, this direction and this direction. And in the next video, we're going to talk about why it takes the path that it does. But really, the vast, vast majority of that current is going to go from here directly into our input. And then our input, again, is going to see almost exactly 5 volts. So again, a little interferences and things like that. It's going to be just ever so slightly lower than 5 volts, but it's going to stay really close to that top there. And that's kind of what our signal is going to look like, well above this threshold that would get us into this dangerous zone in here. All right, so hopefully that kind of helps you understand what a pulled down resistor is. Really quickly, I'll cover actually, I said I wasn't going to, but we're going to cover really quickly what a pull up resistor is. DX, this is again is our digital input. We have it here, and then a node there, a resistor, and then we're going to get this attached to 5 volts. And so you can see pull up resistor. Whoops. And then we have a switch, and this actually goes to ground. So you can see the difference between this circuit and the circuit below. In this case, instead of attaching our resistor to ground, we attach it to power. And that tells our input, like, hey, input, you are constantly seeing 5 volts. But in this case, if it's open, we know for sure that this is a high voltage and that this circuit is closed or is open, that we have an open circuit. But we also have this resistor, which resists a lot of change, or a lot of current, not change. But yeah, so it resists current there. If we close this circuit here, kind of a similar idea. This The easiest path for it to see is going to be this 0 volts because we have no resistor here. So it's gonna essentially see ground, and then it's gonna say, okay, cool. So I see ground, which means that I'm gonna be hanging out here in this low area again. And in that case, a low signal actually means that our circuit is closed, that our circuit has a full connection through there. Remember, in this case, if our circuit was closed here, we saw 5 volts, but in this case, we see 0 volts. So that's kind of the difference between a pull up and a pull down resistor. And you can change the way that a pull up or pull down resistor attached to a button affects your code. And we'll get into code here a little bit later on, but just understand, if you have a button, you want to kind of mitigate the noise that's going on with that button. And so we need a pull down resistor or a pull up resistor. In the next video, we're going to talk about the math that makes this work, and kind of how our current interacts here, and make what's called an equivalent circuit for it, and show how that equivalent circuit, the currents and the voltages through that circuit. So keep an eye out for that one, and thanks for watching.